Okay, so last time we showed that for any transcendence degree 1 field, there is an abstract curve which can also be realized as a non-singular projective curve. It's an if and only if condition. Right, so from now on we can just focus on smooth curves or non-singular projective curves or quasi-projective curves. That I think well motivates now the point of all this abstraction. Any question? Okay, so at this point we can again take stock of the situation in terms of what is the dictionary that we have built between algebra and geometry. So the geometric space, affine space or projective space in fact, versus the function fields. Small k and big K, which is the function field on n variables, transcendence degree n. In fact, I should say here transcendence degree 1 maybe. Okay, we did not do anything with higher dimension. We stayed in curves, so the basically affine projective curves versus transcendence degree 1 fields. So what we have seen is non-singular points right. So non-singular points, you can go from a non-singular point to a DVR. So this OXP is a DVR and in the corresponding function field, and also the rank of the tangent space is 1, right, and you can go back also. So whenever you have a DVR, then how do you go back to a point on the curve? So look at the DVR, look at its maximal ideal, it has a uniformizer, it's a principal ideal. So uniformizer's solution gives you a unique point, that's the point P, right? So you can go back and forth via the uniformizer essentially. And non-singular projective curves and equivalently abstract curves based on a function field. From here you can go to function field and back, right. So actually function fields or transcendence degree 1 fields are in one-to-one correspondence with non-singular projective curves, respectively abstract curves. That also we have shown. And for a tangent space, from a tangent space you can go to the functions on the tangent space, which was the dual, which is also the same as the linear part of the germs that are vanishing at the point. and you can go back from here also. Okay, so in geometry you have tangent space, in algebra you have the germs which are vanishing, their linear part or the dual of the tangent space. These are the functions defined on the tangent space. In the curve case, both of them will have dimension 1. I mean, in the non-singular point case, when P is non-singular, then the tangent space will be of dimension 1, if and only if, and similarly the dual space, the functions defined on this vector space, they will also be dimension 1. If they happen to be dimension 2, then your information is lost. So dimension 2 tangent space means that there is no connection with the point, so the point is actually a singular point. Right, so we have done all this till now. Is that clear?
The constant degree of K of KNK is equal to 1.
No. Yeah, but it's that is not what I mean. I mean, it means that n is equal to 1.
Okay.
I mean, these are two different things. We are looking at the function field of the affine space, in fact, subspace of the affine space, in particular curve. Yeah, but till now, whatever we have done only holds for transcendence degree 1 such objects. We haven't even begun studying transcendence degree 2, and this course we won't be able to do that. For that you need multiple courses after this course. So this is only about transcendence degree 1. But it's an object that lives in this K of the affine space. Okay. Any other questions? So, right, so we will we'll interchangeably use non-singular or simple or smooth. Okay, these things will mean the same now on. So non-singular curve or point, simple curve or point, and smooth curve or point. So, right, so points on a smooth curve. So I want to sketch this geometric picture. You have some curve. And you have the projective line. And this is the curve. So the curve is smooth. We can see the curve as a cover of the projective line. So we want to describe what it means. What we want to say is that, say, look at a point P1 here. So this is related to some point Q1. In fact, we'll show that it's a unique point. So P1 actually covers some point on the projective line for every P1. But sometimes it may happen that so every point on the curve corresponds to a unique point on the projective line. But it can happen that a point on the projective line corresponds to many points on the curve. Okay, so this is called the ramification of Q2. So I will not define it except in this picture, that basically points on the affine line, they can have multiple associated points on the curve. This happens because for example, in the case of y square equal to x cube, for a single x you have two y's, okay, because you have two variables on the curve instead of single variable. So when you fix a variable, the other variable may take many values. So that is why this cover, it's actually a ramified, in general it's a ramified cover of the line. But this picture is typical, this is what happens. And so this thing is called a cover. If K is algebraically closed. So let us see a proof sketch of this. So any point P that you take on the curve, how do you show that it corresponds, I mean, what is the point you should associate to on the projective line? So formally what you should do is, since P is a smooth point, you look at its DVR and look at the uniformizer, and the solution of that is the point on the projective line that this should correspond to. So we set up that mapping. So point P has a DVR. This O of CP, and in fact I can just assume the setting here. The setting I should have written, so K is contained in Kx is contained in the function field of the curve. Okay, so the projective line is coming from this Kx, and the big K is giving you the curve, and small k is the base field which is algebraically closed. So this is the setting. So in this setting, actually, when you get the germs OCP around the point P, you should take intersection with Kx. That will work.
I want to just confirm something, that the smooth curve is projective, right? I'm assuming that.
Smooth curve is projective, yeah, sure. But if you remember, the projective is needed only because there is one extra valuation. This valuation because of 1 over x.
Every non-singular curve is isomorphic to projective curve. We don't know if it's isomorphic to a affine curve.
Yeah, sure. And that was only because we went via the abstract curve. In the abstract curve, there was one extra valuation. So all the infinitely many valuations except this one valuation is what we cannot realize in affine, because it corresponds to this fraction. It doesn't correspond to polynomial. The fraction being 1 over x. So that requires, its solution is basically 1 over x equal to 0, which means x equal to infinity. So that is called the point at infinity. So which is why you need a projective curve, because it will have a point at infinity concept. Yeah, otherwise all the discussion will be the same as affine curves. So when I say point P, you can think of it just as an actual point on an affine curve. Basically, you take the affine open. In the affine open patch, so you get this DVR, and you look at the elements which are in Kx. Take the intersection. Right, so let's take the intersection with kx. This also is a DVR. It's a DVR in kx now, which gives you the unique point. Via the uniformizer. Okay, so this projective line, its field which is contained in your curves function field small kx. When you take the intersection with this field, you get a DVR which gives you the unique maximal ideal, which is principal, and the generator gives you the point. Okay, so this is the association in one direction. Curve point gives you a point on the projective line, and the converse of this will be similar. So now let's take a point Q on the projective line. This gives a DVR inside the function field of the line, which is small kx. Then extend it to R tilde inside the big field. Right, so a DVR can be extended to the full function field. We had seen this. It's basically the integral closure inside the big field, and this may not be unique. So there may be many R tildes. So you pick one R tilde, and its maximal ideal gives you the point on the curve. So in this case, R tilde and P are not unique. Okay, so this is the reason we have this now both ways. So when you go from curve to the projective line, you get a unique point. But when you go from the projective line to the curve, since there are many possibilities of extending DVR, you get multiple points, and that is called ramification. Okay, so it's a cover that possibly ramifies. So possibly multiple points on the curve are covering a point on the projective line, but every point on the projective line gives a point on the curve. Okay, so this, as you can see, the proof is not very trivial. It needed all this machinery, but in the end, what this is telling you is something very important, that these smooth projective curves, they are actually very tightly related to the projective line. And since in the end of the course we want to count points on the curve, somehow that counting will be inspired from the count on the projective line. Okay, so projective line has how many points? It has P actual points and one point at infinity, P plus 1. So in the end of the course, we will show that any smooth projective curve has points almost P plus 1. Okay, it will have points P plus 1 plus minus square root P. So the whole course is to show this square root P error. Okay, that is called Riemann hypothesis. So we ask this question and we'll answer it before the course ends. So this finishes the proof, and the question now from now on is this: for finite field FQ, what is size of the curve restricted to FQ points, coordinate should come from FQ, minus the projective line on that space. So what is this? Okay, that's the question. And this of course is equal to Q plus 1. Right, so the motivating question of this whole course, and in fact much of modern math, is how far away can the points on a smooth projective curve be from Q plus 1, the points on the line. So some of the picture doesn't give you a very good idea, because every point on the curve may have many possibilities of PIs. So it seems that the curve may have 2 times Q or 3 times Q or 100 times Q many points, but we'll actually show that that's not true. It has almost as many points as the line. Right, so that's a very surprising thing, and very difficult to actually conjecture. Okay, so that will prove in generality for curve case. If you are interested in higher dimensional objects, surfaces, etc., then that, as I said, is a much harder topic. It requires many courses. Okay, that we won't be able to sketch here. But even that is inspired from what we will do in this course. This was done first by Whale. Okay. Yeah, so I need some definitions now. So think of K as FQ for this definition. Okay, it is definitely not algebraically closed. So in this case, we need some more definitions because things are not that nice. At least what is true, what still holds, is that a point defines a valuation P on the curve, defines a valuation VP on the function field given by OCP. This continues to be true because this fact was just based on this ideal that is defining the point. And yeah, so the point of course always is in some finite field, even if your small k was algebraically closed. Still, when you look at a point, the coordinates are finite, so they are always in some finite field. So the valuation is the same as we worked with before, but there is another thing which might change, which is the residue field. So residue field at P will be called Kp. It's the quotient of this jumps modulo the jumps which are vanishing, right? We have seen that this is a field, but in the algebraically closed case, this was itself small k. Because from an algebraically closed field, there is nowhere else to go. If you want to go to algebraic extension, you will stay in small k because it's algebraically closed. But here, since now our small k is a finite field, this thing may be bigger. Okay, there is no reason why it will be equal to small k. So it may be bigger. This is the different thing that can happen when your field is not algebraically closed, or when it's a finite field. That at a point, although the point is coming from the same finite field, but the functions around may take you further away. So from GFQ, you may go to GFQ Q square or Q cube or wherever, bigger field. And hence we should take care of the degree. So the degree of a point is dp, sorry, not this p. How far is this field from the base field? Okay, so that's the degree. Is this clear? So if you go from GFQ to GFQ square, then the degree, for example, is 2. And if you go from GFQ to itself, then the degree is 1. So in the algebraic closed field case, degree is always 1. Now it may not be 1. Okay, so that's the big change that can happen. So first is degree of a point is always finite. That's an easy property. Second property is if you take intersection of all possible powers of these maximal ideals, you get what? Can there be a function which is present in all these powers, mp to the I? We'll show that the only thing that is present is 0. Third property is so MP gives a uniformizer U then the relationship between the uniformizer and the valuation that the point defines, right? The relationship, as you can guess, it is the highest power of U that divides alpha. So I can write it formally as alpha contained in U raised to I OCP. Okay, so the third property is saying that for the generator of this principal ideal and the valuation, the connection is that for all field elements, Vp alpha is equal to the largest power of U that divides alpha. So these things continue to hold. For what is the first proof of the first property? So how do you show that the residue field is finite degree? So let U be the generator. Okay, let MP be generated by this uniformizer U. Consider all the rational functions in U. So they are clearly contained in the big field, transcendence degree 1 field. Now, what is the connection between the degree, the dp, and ku? So the claim is that the degree is equal to the degree of this. This is an algebraic extension. Finite. It's a finite algebraic extension simply because U is transcendental over the base field and big K has transcendence degree 1. So once you have introduced the transcendental element U, what remains is a finite algebraic extension. So that degree is actually equal to the degree of the point. Do you believe that?
Why does this algebraic extension need to be finite?
No. So yeah, that's a good question. Because the functions I am looking at are also coming from small k. They are not coming from the algebraic closure of small k. Then it would have been infinite. So the big K is actually the functions from the same field. Like if it was a finite field FQ, we are looking at functions from FQ. So the constants are the same. Yeah, think about that example. In the example, can we see this easily? So U essentially comes from the definition, the ideal that defines the point P. No, I think I maybe misspoke. I think the point on the curve here is arbitrary point. It's not coming from GFQ. Yeah, I think this can be anything. So the curve here is actually coming from K bar. Yeah, and then these objects OCP, MPP, MP are actually coming from K bar. But let me clarify this next time. I will not need the degree thing anyways today. So let me skip these details for now. Let's move to the second property. So let Y be an element in the intersection. Right, so this means that the uniformizer raised to I divides Y for all I. Correct? So essentially infinitely many powers are dividing Y, but Y is ultimately it's just a element in the function field, right? So it's a finite object. So infinitely many powers, I mean it is impossible to be divisible by U raised to infinity. At some point the division will stop happening and after that it will never happen. So basically there are finitely many I's for which this can happen. So that's a contradiction. Okay, so the only thing, or in other words, this means that Y is 0. Okay, 0 is the only number function for which this is possible, otherwise it's not possible. And third property, which is generator of the principal maximal ideal MP, is related to the valuation that way. This is clear from the way we had defined valuation anyways. Yeah, so this degree thing is the only property which is messed up. I have to clear this proof next time, because next time we'll start a new topic where this will be useful, which is the divisor class. So today we'll not do that. What we want to finish today is so any f in the function field of a curve gives you these numbers. Right, so a function corresponds to this infinite array of integers. These can be negative, positive, or 0. So the question we want to answer: can we go back? If I give you an array of infinitely many, VP values for every point P, is there a function which corresponds to this infinite array? Given RHS, does there exist an F? Okay, so given the like candidate valuations, is there a candidate F that matches them? So we will show that
Algebraically closed field.
For this, yeah, you can assume any small k. So you can assume algebraically closed. Yeah, we will not work with degree yet, so you can just assume small k to be algebraically closed. And it's not an algorithmic question yet. It is still, even the mathematical part is currently not clear whether an F exists. Does every array on the right hand side corresponds to a function in the left hand side? Or are there holes? So there are these arrays which actually don't correspond to a function. So these are holes. Now what I am getting at is that actually there will be holes, and based on the dimension of the holes we will define genus. Okay, so that we will do after a month. But this is the starting point of understanding what holes are in a curve and how can we measure them, how many holes are there. So it is we are doing this work in the direction of genus definition. So we will now show that F can be reconstructed from not from, matching, reconstructed, that matches a finite part of RHS, but not all. Okay, so we'll show that if you care about certain points, certain valuations, finitely many, then those values can be matched by a function. But if you care about all the values simultaneously, then it may not be possible and F may not exist. So we'll prove this approximation theorem. approximate valuations theorem. So let K be the function field of a curve. And whenever we'll say curve, we'll mean smooth curve. So I'll not mention it from now on. Let P1 to PH be the points that you care about. With the corresponding valuations V1 to VH. Okay, so remember that the field is algebraically closed, could be algebraically closed, so the number of points is infinite. But in this hypothesis, we only care about finitely many points, H many points. So let's call them P1 to PH, and the valuations they define are V1 to VH in the abstract curve. The abstract curve has all the valuations. And let U1 to UH be some functions given to you, and some numbers given to you. Okay, that's the hypothesis, the premise of the theorem. What we will show is there exists a function such that for all these i's 1 to h, the ith valuation of u minus ui is at least mi. Okay, so this is the approximation theorem of valuations, finitely many valuations. It has some extra data, like these ui's are also there given to you, and mi's are given, and you want a single function u such that the difference of u with ui, that valuation is at least mi. Okay, it's phrased a bit differently than the question that I had asked, but actually the question will be answered from here also. We'll see that very soon. Is the statement clear? It's a highly non-trivial statement. It may as well be false because the numbers mi's are arbitrary, right? And the points are arbitrary, the valuations are arbitrary, and you want a function that matches all these things. There is no reason why that should happen, because the curve is also arbitrary. Right? So this is a very general statement. You can't really see this from geometry. It's a purely algebraic fact. So we'll prove this in steps. So okay, we will prove this by induction on H. What's the base case? H equal to 1. So you are given a point, there is only V1, so you want V1 u minus u1 to be at least m1. How do you do that? You want to solve for u1. Can you solve it? You want to solve for u. Everything else is known. Point is given, u1 is given, m1 is given. Can you find a function f such that v1f is at least m1? I mean, of course you can take the uniformizer of the point p1 and raise it to m1. So uniformizer needs something else. Let's call it alpha 1 maybe. Consider U to be U1 plus alpha 1 to the M1, right? This is simple because now U minus U1's valuation is exactly M1. So you have matched it exactly, right? So base case is easy. What is not easy is the induction step. So now we'll assume that the theorem holds for H minus 1, and we are trying now H. That's the induction step. We want to prove it for H using H minus 1. So for example, when H is 2, what the problem is that you have two constraints, V1 U minus U1 at least M1 and V2 U minus U2 at least M2. This solution which we found before, it's not clear how do you modify it. So I mean, even if you forget U1 and U2, we set them to 0. What we have done is U equal to alpha 1 to the M1. So next time you should try alpha 1 to the M1 times alpha 2 to the M2. Right, that kind of thing you should try. But it will not work generally, because when you compute the valuation, maybe alpha 2 contributes something to V1 and alpha 1 contributes something to V2. So you have to do this more systematically. Plus there is this additional thing of U1 being present. So this is not so simple as the base case. So yeah, so now we are in the induction step, and here I can prove a claim. Actually many claims. First claim is that given integers E1 to EH minus 1, there exists a U such that for all I 1 to H minus 1, VI U is equal to EI. Okay, that's the thing I had promised in the question, that if you are given numbers, potential valuations, then I can give you a rational function which will match them. So VIU is equal to EI. Okay, I'll get this basically from this theorem which we are assuming in the induction step, in the induction hypothesis, which will in the induction hypothesis at least we have answered the question, and then we'll use this to complete the induction step. So again, read the theorem statement for H minus 1. Can you deduce claim 1? So here is the proof. Find Wi's such that for these i's, H minus 1 i's, VI is equal to EI. This is easy because Wi depends on I, right? So this is just the thing we did in the base case. So Wi you can simply take uniformizer alpha I to the EI, right? So Wi you can construct trivially. So consider those Wi's, and Now set up the system for the theorem. Consider the system 1 to h minus 1. You have Vi u minus Wi greater than equal to Ei plus 1. So, by induction hypothesis of the theorem, we get u in the function field. Okay, so the induction hypothesis of the theorem will give you a u such that the difference of u and Wi is at least Ei plus 1. Right, that's the theorem statement. Which means what? Which means that the valuation of what was claim 1? You want to look at valuation of u. So what is valuation of u? Valuation of u is valuation of u minus Wi plus Wi, and now you use the additive nature of the valuation. So u minus Wi has a valuation Ei plus 1 or more, while Wi has valuation only Ei. So this valuation is Ei. Okay, so the theorem immediately gives you this u which we asked in the question. Okay, so for h minus 1 valuations, they will be matched if the theorem is true. The theorem for h minus 1 is true. That was the claim, so we have proven the claim now. Okay, so now we move to the next claim, which is that V1 to VH are Q linearly independent. Now this is a statement interesting on its own, because we are saying that if you take distinct points, then the corresponding valuations are somehow, they are very different. In particular, there is no linear combination of these functions which vanishes globally on the function field. So suppose not. So then let a rational linear combination vanish. So what you can write is this equation VH, let's say VHU equal to sigma Ri VIU for all u in K. For some R bar in rationals. So let R1 to RH minus 1 be some rational numbers such that this identity holds for all u. Okay, the valuations are basically linearly dependent. We are assuming that. So we want to get a contradiction from here. Do you see an easy contradiction? Yeah, we don't see an easy contradiction because everything here is arbitrary. We don't know anything about the valuations or the curve, so we have to do this in a bit deeper way. So let's look at the case of H equal to 2 and R1 positive. So we are saying that V2 is a multiple R1 times V1 and R1 is positive. What this means is that the DVR for V1 and V2 are the same, right? Because DVR comes from positive, non-negative valuations. So this means that if you look at the Z's, for which V1 is non-negative, V2 is also non-negative. Right? Is that clear? Because V1 is just, let's say V1 is 2 times V2 or 3 times V2. So in that case, you can see that if one is non-negative, the other is also. So you get the DVRs to be equal. And what happens when the DVRs are equal? Yeah, so DVRs give you the uniformizer are the same, so points are the same. Which is not the case. Points were different, valuations are different. So DVRs are different. Okay, so now you get some handle on this thing. At least you have understood that why are V2 and V1 very different. But only when R1 was positive, R1 can also be negative. Then what do you do? So then we have to give a different proof. So let's take R1 to be negative, and H can be anything. I will not need H to be 2. So that the other case is R1 negative. In that, what you have to do is find ZZ prime, two functions, such that for all I 1 to H minus 1, the following happens. So VIZ should be 1, while VIZ prime should be 0 if Ri is non-negative and opposite otherwise. Okay, so now just looking at 1 point won't be enough. So we want to construct 2 points which should somehow contradict the linear dependency that we had before. And this system is basically dependent on the coefficients, these Ri's. So for the non-negative Ri's, ZZ prime has that valuation 1, 0. I mean, essentially, Z is identifying with non-negative Ri's, while Z prime is identifying with negative Ri's. Yeah, and this should give a contradiction. But why will they exist? That we have shown in claim 1, right? So just look at the system for Z. You want valuations to be 1 and all 0, the rest 0. So you know that such a Z exists, and similarly Z prime exists where it's 0, 1 in this distribution. Yeah, so they exist. That's from claim 1. Yeah, so because we are asking only for 1 to H minus 1. So that was the induction hypothesis based claim 1. Once you have this, what can you deduce? Now you look at the red equation and check VH of Z. What is that? So VH of Z is, so Z identifies with non-negative, right? So hence VH will be greater than or equal to 0. And VH of Z prime identifies with negative. So this will be negative. So we are using the additive nature. Property of valuation. Right? This is how we had designed Z and Z prime. Now what is the contradiction? Where will that come from? So for the contradiction, you have to look at Z plus Z prime. That's where the contradiction will come from. So Vi of Z plus Z prime is what? See, Z is non-negative, Z prime is negative valuations, and the valuation of sum will be then the least. Will be. Oh yeah, actually they are different. So since they are different, it will be the least one. So that will be negative. No, wait, something is wrong. It will be. Then the minimum one or the.
It will be 0 and follow the.
It will be 0, yeah. Sorry, I should have said what I is. I'm thinking of I equal to H. No, I want I 1 to H minus 1. I'm looking at this. So for example, V1, so I mean Vi, so the above part, in the above part, you know that Vi of if you look at the Z valuations, they are. I guess you just have to compare 1 and 0 and pick the smaller one. So that will be 0. So you get 0. Is that clear? Because Z and Z prime, the valuation is always different. So you just pick the minimum one, that will be 0. And which means what? Yeah, so 1 to H minus 1 valuation is 0. So you get for VH by the red identity also 0. Do you actually get 0 or greater than or equal to 0? And then what?
Why greater than?
It's they are all equal, right? So for example, 1 minus 1 valuation jumps from 0 to infinity. So I only get greater than or equal to 0, but now what? Sorry?
About above that VH is Z greater than equal to 0 and VH is Z prime less than 0, then which is Z plus Z prime is.
Yeah, so I did not deduce anything from there. Now I use that. Also VH Z plus Z prime is the minimum of VH Z because they are different, and the minimum one is negative. That's the contradiction, right? So the orange part tells you that it should be negative, the black part tells you that it should be non-negative, so you get the contradiction. Yeah, so after all these calculations you have shown almost independence. Is there any case remaining? For H2 I have handled positive and I have handled negative in all the cases, so what remains is let's say H is equal to 3 and both R1 R2 are positive. Those kind of cases still remain. That's the last case. Each
Did we use the fact that R1 was negative? I think we didn't use it like anyway.
No, we must have. No, we did, right? Because this orange premise is non-vacuous. See, we are using that to get the negative sign. You have to have.
Yeah, got it. For these two.
Yeah, exactly. The middle orange one, you actually want negative sign. So that's where you use the non-vacuous nature.
At least one negative you want.
Exactly.
So then V is 0, Z will not be equal to 0 because V1 of Z is 0 and there will be negative and positive terms both. So,
Sorry, where? What?
when you take VH of Z,
VH of Z, yes. So VH of Z, only look at the Z values. VIZ is 1 when Ri is non-negative, otherwise it is 0. So what it does is that it kills all the negative coefficients. Only the non-negative, in fact the positive ones survive. And from the positive ones you get. Yeah, so just one case remains, which is H greater than or equal to 3 and all the Ri is positive. This is the case remaining. So basically this V3 is dependent on V1, V2, but both of them are positive. That's the case we are left with. In that case, you just rearrange the equations to have a negative sign. That's all. So for example, you rewrite. Yeah, you just rewrite V1U in terms of V2, V3. So in fact, the rest, so VH. So this implies that you are in the previous case. So that's all. Okay, so all the cases are there. Hardest case was this one, where your R1 was negative. There you really need the full power of the induction hypothesis. Is that clear? Okay, so we can't finish the theorem, I guess. Let's do it next time. So after this claim, what we will do is, we want to do the induction step. So we want to construct this U, and we'll construct it in the following form. sigma xi ui for rational functions xi. Okay, so you in the conclusion of the theorem, what you want is you want to study you want the valuations u minus vi of u minus ui. So for that we'll instead find these xi's. Okay, so the thing that we'll study is actually this. So for example, if you look at v1, what this is, x1 minus u1, x1 minus 1 u1 plus xi ui I equal to 2 to h. Okay, so we'll control these valuations, this valuation and this valuation. We'll design xi so that this xi's and xi minus 1's, their valuations are in control, and then from that we will get we'll finish the induction step. What we want is this thing to be greater than equal to mi, so we'll take care of that next time.